Welcome to this tutorial. In this tutorial, we focus on Aspen Plus simulation of a regenerative ideal Rankine cycle with one open Feedwater, and we try to optimize this open Feedwater heater. Just to recap what we discussed before about open Feedwater heater, basically this type of Feedwater heater is a mixing chamber where the steam is extracted from the turbine and then it mixed with the feed water that exit from the pump after the condenser. Afterward, we add an extra pump and transfer this feed water to the boiler. In ideal situation, the mixture after the open feed water heater leaves here, state number 3, leaves the heater as a saturated liquid at the heater pressure, which is the same as the pressure of the extraction. Let's do this with one exercise. Consider we have a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees C, and it's condensed in the condenser at a pressure of 10 kilopascal. First, we want to find the optimum amount of the extraction from the turbine at a pressure of 1.2 megapascal if the feed water leaves the heater as a saturated liquid. In other words, we have an ideal open feed water heater. The steam flow rate is 10,000 kilogram per hour, and we know that the saturation temperature of water at 1.2 megapascal is 188 degrees C. Let's do this in Aspen. We start modifying a previous simulation that we did together. If you haven't watched that video, please watch that video. In that video, we added one open feed water heater to an ideal simple Rankine cycle. If you remember in that exercise, we assumed that we extract 20% of the turbine steam at 1.2 megapascal or 12 bars. So as you can see here, the split fraction is 0.2 for the extraction stream. And to make this simulation, we added an extra turbine, but in reality, these two turbines are one turbine. We just did this trick to perform the simulation in Aspen. Now, if you check with the current numbers that we have, if you check the temperature of the feed water after the open feed water heater, you see that the temperature is 181, given the fact that we have extracted 20% of the steam. Now we want to see how much extraction do we need in order to reach the saturation temperature at 12 bar or 1.2 megapascal, which is 188. Obviously, we need to increase this value. You can do it in two different ways. You can just do this by hand. Every time you change the value here, you'll rerun the simulation and you check the temperature. The other approach, which is very, very useful, is to use a tool in Aspen that is called Design Spec. So here, if you go to the flow sheeting options, we have an option or a tool that is called Design Spec, and we try to use this to modify our simulation. If you click on Design Specs, here you create a new design spec. It's named DS number 1. I keep it as it is. You can rename it if you wish. And then we need to define needed parameters and information for the program. What is design spec doing is that it varies some variable for you in your simulation in order to reach a criteria that you define for it. We do this in input. In the define, what we want to do is that if we want to change the fraction in the splitter until we reach a temperature of 188 after the open feedwater heater. So we go to input, and then you define the variables that you want to target. Here is we have the temperature of the open feedwater heater. Uh, so you click on OK. It's stream variable. So you go to stream variable, and then you select the open feedwater out, and then the variable is the temperature. And let's assume the unit is degree C. In the spec tab, we need to specify the targets. So we want to have the temperature of 188. So let's define that 188 here. And our spec here is the temperature of the feedwater. Make sure that you do not make typo errors here. It's quite common. So make sure that you have correct spelling of your parameters. So TOFW, so TOFW is equal to 188, and the tolerance, let's say, is 0.1. One point here is that the saturation temperature of the water at 12 bar is not exactly 188, it's 187.96. So it's better because we have a pump here right after open feed water heater, so make sure that you have no vapor in the inlet of the pump because it will damage the pump. So let's say that we put some margin here. Let's say that the target is 187 because it's because then you're safe. The tolerance, let's say, is 0.1, and in vary we have a block that we want to manipulate, and the block variable that we want to manipulate is in splitter. The variable is fraction, and the stream is x t, because this is the extraction in our flow sheet here. If you see here, this is the ext. So we go back to the input. Here, the lower limit, let's say that the lowest value is around 1%, and we go up to 50%, so 0.5. So this should be okay. And now we reset the simulation and we run it. So the results now are available. So you go to the Design Spec result here, and you see that the final value is around 21%, very close to the value that we had before. So we go back to the main flow sheet and we briefly check all the temperature and pressure and double check if everything makes sense. So here you can see that that's the pressure of 12 bar. We extract some steam around 21%, and then now the temperature is higher, and it's very close to the saturation temperature of 188. This was the way that we can use the design aspect. Let's continue the same exercise, and we add one more criteria. Let's say that we want to do the simulation for exactly the same steam power plant, but the difference in this second step is that we also want to find the optimum pressure, because every time that if you change this pressure, the pressure of the open feed water will change, and it will affect the pump number 2, and of course the energy and mass balances. Now we want to see how we can find the optimum pressure and also the optimum amount of the extraction from the turbine, assuming that we have an ideal open feed water heater. Let's see how we can perform the simulation in. What we want to do is basically something like a sensitivity analysis. as we did before. If you don't know how to do it, please watch the previous video. We want to see if we change this pressure, how the overall efficiency of the cycle changes, because the optimal value for the extraction and the optimum amount of the extraction the, actually is the value that gives you the highest cycle efficiency, because eventually this is the point. That's the point that we add this open feed water heater and closed feed water heater to the simple ideal Rankine cycle. Uh, so we can perform a sensitivity analysis, but we have an issue here. Every time that you change the pressure, because when you do the sensitivity analysis, what you can do is that you can ask the program to change the discharge pressure of turbine 1 and then tabulate the value for efficiency. Every time you change this pressure, you also need to perform this design spec in order to find the optimum amount of extraction for that given pressure in order to get the same saturation temperature. Because when you change the pressure here, the value for the saturation temperature changes. So let's see how we can do this in Aspen. What we can do is that we can add a heater and a cooler and heater here just right after the turbine number 1. And we can ask the program to remove the heat from the steam until it's saturated vapor liquid, and then add back this to the stream using a heater. And in the stream in between these two heater and cooler, every time that we change the pressure, we can have the temperature of saturation. So basically, instead of using the steam tables every time, we do this automatically in Aspen. I pause the video and I add this heater and cooler here, and I rename the streams and blocks, and then we take it from there. So now we can see that I have added a cooler and a heater. There are two simple heater that I've taken from this option here. And then I have connected the turbine to the cooler, and after that to the heater, and then after that to the splitter. And then I used the energy stream heat. I took out the heat from cooler and put it back to the heater. When you run the simulation, I will show you. You will see that in this stream that I call it the REF or reference stream, you can find the saturation temperature at the given pressure of the turbine 1 output. Because the way that I set the settings here, I can show you. If we click on the next, then we are navigated to the cooler. In the cooler, the pressure drop, I set it to 0. And then instead of temperature, I take the vapor fraction and I put it to either 0 or 1. Both are fine, no problem. So if you take, let's say, if you take 0, then the heat is removed from this stream, T1 out, until it's a saturated liquid. And when it's a saturated liquid, it's the temperature of saturation in that given pressure, because pressure drop is 0. So before and after the cooler and even heater, the pressure is the same. So for the heater, we only need the pressure drop, and it's equal to 0. This is enough because I already connected the heat stream from the uh, first cooler, sorry, here to the heater. So let's run this and double check the temperature and pressure. So I run the simulation, and this run includes also the design spec. So here you see that the temperature is 188. If you double click on the reference stream, you will see exactly the temperature of saturation at 12 bar is 187.9, almost 188. Those decimals are not shown here in the in this team. But what I want to, what I try to say is that when you change this discharge pressure, then the program automatically can read the value of saturation from this stream, and that's the trick that we want to do. Now let's continue and see how we can modify the design spec in order to get the proper settings. So if we check the settings that we put in the our design aspect number one, which was changing the splitter fraction until we get a value of 187. Because if you want to perform sensitivity analysis, we need to change the pressure in a range as the outlet pressure of turbine number one, which means that every time we have a new value for temperature, so the settings that we have right now is not correct. So one way to modify this is that we add one more parameter, and that is the temperature of the reference stream. It's stream variable. Stream is a reference, and the parameter is temperature. Uh, Now in spec, you can modify this. So we say that the TREF, or the temperature of the reference stream, minus the temperature of the open feed water heater, let's say that it's around 1, which means that the program will read the value of the temperature from this stream, and then it calculates this TREF minus T open feed water. Since this value, I mean, basically the target should be 0, but as I mentioned, since we have a pump, we take 1 to be on the safe side. And then the program will, uh, perform the analysis. So let's reset and rerun this before we do the sensitivity analysis, just to make sure that everything works fine. We have no typo or no strange issues here. So here you see that again we have the 187, and in the results we see we have around 21% as the final value for the extraction. So if we extract 21%, we get the temperature that we want. There is one more thing we need to take care of, and that's the discharge pressure of pump number one. Because if you follow the streams from the turbine to the condenser and afterward to the open feed water heater, in the settings of the pump number one, we set the discharge pressure to 1.2 megapascal. And later on, when we do the sensitivity analysis, if you change, for instance, the discharge pressure here from 1.2 megapascal to 2 megapascal or 3 megapascal, then the discharge pressure is still the same as before in pump number one, which will cause some issues, and you will get a lot of errors and problems. And in order to solve this problem, we can use a tool in Aspen, and that tool is called Transfere. So what we do is that we click on Transfere and we create a new transfer. Let's call it T number one. And here we want to transfer the discharge pressure of turbine number one to the discharge pressure of pump number one, because the discharge pressure here is the same pressure as the open feed water heater, right? So here we want to change the block variable, and the block is turbine number one, and we want to transfer the pressure here. We look for pressure. Here is the specified pressure, outlet pressure. Units is in bar, and we transfer the same to the block. We make a new variable. It's a block. The type is block variable. The block is pump number one, and the variable is pressure. So specify outlet pressure. So if you do that, then you are safe. Every time you change the pressure in the turbine number one, it will be automatically transferred to the pump number one as well. So let's run the calculation once and see if everything works fine. Yes, it works fine. Just to double check, I will change the discharge pressure here from 12 bar to, let's say 13 bar or 1.3 megapascal and see what happens. Maybe 1.1, I go for 1.1. And then I reset and rerun the calculations. It's always important that you check everything afterward when you make a change in your simulation. So here the pressure, the discharge pressure now is 11 bar. You see that the discharge pressure of the open feed water heater, sorry, pump and open feed water heater is 11. And the temperature, since we decreased the pressure from 12 to 11 bar, the saturation temperature changed from 188 to 184. And we set 1 degree less in output of the open feed water heater in the design spec number 1. So everything looks fine. So we continue and add the sensitivity analysis to our design. And now it's time to do the sensitivity analysis. Uh, Here in the model analysis tool, we have the sensitivity analysis. We create a sensitivity analysis. We name it S1. We need to define the variables. So here we need to add the variable that we want to vary, and that's the discharge pressure of turbine number 1. Here, as you see here, because this will affect the open feed water pressure, and we want to see what is the optimum pressure. So we go back to the input of the sensitivity analysis. The type is a block variable. We pick turbine number 1 and the pressure here, and then unit we keep it as it is, a bar. And start point, we have 11 bar, so 1.1 megapascal. So let's say that we start with 11 and we go for 13. And then increment, let's add like 0.25 as the increment. And then we need to define the variables because the point is to change the discharge pressure of the turbine or the extraction in order to get a higher efficiency, right? So the factor that we want to investigate would be the efficiency. We already have added these variables in the calculator, so we can copy and paste these variables. We select those variables and we copy, and then we go there and we in the define we paste those variables. These are the needed variables to calculate the efficiency of the cycle. We also can take the uh, equation for calculating the efficiency. So I just copy and paste those things here. So here I add one column, and then in that column I want to tabulate this value, which is the efficiency of the cycle. Now let's run the simulation and see what do we get. So we run the analysis and we wait for the results. Results are available. Fortunately, we got no errors, so we go to the results. Here you see the value for the efficiency in the last column by varying the pressure and the units is in bar. So in order to have a better look, we can select the efficiency versus pressure diagram, and we see that we have got a nice curve, and the maximum in this curve is around 12.1 is this point. That's 12.5 this point. So it seems that 12.5 is pressure in which you will get the highest value for your efficiency, and it's around 34.6. If you want, you can narrow down the range that you have selected here and test it one more time and see how it works. But I don't think that is not needed here. But if you want, you can perform that. Thank you very much for watching this video. I hope you have learned how to use the design spec and transfer function in Aspen, and we continue in another video.